Hello everyone, today our team will present a case study on improving LCD mirror defects using the Lean Six Sigma DMAIC methodology. First, about the background. LCD screens are key electronics components and their display quality directly impacts the user experience. It makes quality measurement a core competitive advantage in the manufacturing industry. This led to our core issue, the mirror defect. As these images clearly show, this isn't a single problem. It's uneven screen brightness that can manifest as spots, lines, or entire regions. This is a major quality flaw. In our specific case, a high mirror rate led directly to a surge in customer complaints, which were seriously hurting the product's market competitiveness. Our approach to solve this problem is Lean Six Sigma. This methodology combines Lean's focus on eliminating waste with Six Sigma's focus on reducing process variation. We follow the five-step DMAIC model to structure the project. Let's start with the define phase. Our project chapter was to fix the high mirror rate on a specific frame-mounted LCD product. We defined a defect as any screen with over 10% non-uniformity. And our goal was clear: to significantly reduce the defect rate from its initial 3.9% down to under 2%.
In the measure phase, we first figured out the key process parameters that affect the mirror defects, things like machine alignment shift, lamination pressure, and flatness, plastic shear deformation, and holding time. To make sure the later analysis is accurate, we use the GR&R analysis to carefully check the measurement system and confirm its repeatability and reproducibility are solid. Only when the measurement system is reliable can we pinpoint the real sources of variation accurately and lay a credible data foundation for the analyze phase. We checked the measurement system stability with GR&R analysis, got a 14.47% score, which is grade B. That means its repeatability and reproducibility are acceptable. We also did a two-way ANOVA test. No big differences between operators, and the parts don't interact with operators. So the measurement results mainly reflect real differences between parts. Long story short, the measurement system works for telling part variations apart and meets this project's data needs.
Now let's move to the analyze phase. Our goal here was to find the root causes of the high mirror defect rate. First, we use a tool called a fishbone diagram. This helps us brainstorm all possible reasons in a structured way. We look at 6 main areas: man, machine, method, material, measurement, and environment. For example, under man, we thought about improper handling. Under machine, we identified pressure imbalance as a key suspect. Under method, we look at the lamination process and pressure holding time. The most important area was material. We strongly suspect that plastic shear deformation was a major problem. On this slide, we move from ideas to proof. We use data to validate our suspicions. First, we look at screen flatness. We took 2 groups of samples, one with good flatness and one with poor flatness. The data showed a big difference. The mirror rate for good flatness was only 4.6%, but for poor flatness, it was 9%. We ran a statistical test called a two-proportion test. The result gave us a p-value which is less than 0.05. It means the difference is real and significant. Next, we look at plastic shear deformation. We measure the deformation of many shears and check their mirror rate. We saw a clear trend. More deformation leads to a higher mirror rate. We use regression analysis to model this relationship. AI tool gave us a clear equation and the key number R squared, which is over 92%. This is a very strong relationship. So in summary, we have now used data to prove the key root causes. Now we are ready to propose improvements.
In the analysis phase, we collect data from 3,000 samples to test our hypothesis. The table clearly shows a direct correlation. As the plastic shell deformation increases, the Mura defect rate rises significantly. This indicates that deformation is a key factor. We confirmed this using a linear regression model. The p-value is 0, and the adjusted R squared is over 92%, which proves a very strong relationship. The analysis confirms that plastic shell deformation is the root cause of the Mura defects, as it leads to uneven pressure during lamination. Moving to improve phase, we focused on reducing plastic shell deformation through 3 actions. We initiated stricter supplier screening. We tightened incoming inspection by lowering the AQL from 0.65 to 0.4. We added a mandatory deformation measurement steps during the production process.
Then let's talk about the control phase. Our goal in the control phase is simple: make the improvement stick. We focused on 3 key actions. Firstly, standardization, creating and implementing clear SOPs for lamination and assembly to ensure consistent, repeatable operations. Secondly, prevention, introducing equipment calibration checklists to maintain optimal press balance and prevent a key root cause of deformation. Thirdly, vigilance, tightening inspections at both the incoming material and final product stages, creating a multi-layered monitoring net. So what's the result? A sustained and significant drop in the Mura defect rate, from 3.9% down to a stable 1.2%. This proves our solutions are effective for the long term. Finally, in conclusion, the project successfully applied the Lean Six Sigma DMAIC framework to solve a chronic quality issue. We confirmed 2 root causes. The first one is plastic shell deformation from the suppliers. The second one is excessive lamination pressure and time. The results were clear. Firstly, a 69% deduction in the Mura defect rate. Secondly, greatly improved process stability and low costs. This case proves the power of Lean Six Sigma for a complex manufacturing problem. The method is not just for LCDs, it's directly applicable to other high-precision industries like OLED and micro-LED, providing a valuable blueprint for future quality improvements. This is all of our presentation. Thanks for your listening.